This is note packet number 3. We're going to start by talking more about the idea of things being relative to each other. Usually the best types of scenarios to look at are scenarios where money is involved. So we're going to look at the scenario here where there's investments. So I'm going to put my name on here. My original investment is $140. I'm going to put Jamie here. And then the third one I'm going to put Tracy. Okay, so we're looking at 3 different investments, 3 different quantities. The quantity that I invest is $140. And if I'm looking at the actual change, I actually have to look at the difference of the end value and what I started off with. So in this case, the actual change was $80. We're not going to look at the relative change yet because we're just going to find the actual change for the other 2. This one here, if I take $650 and subtract the original investment, they made $150. And if I take $1,100,000 and subtract the original investment, they made $100,000. At this point, I would ask you who the better investor was, but we don't have enough information to say that yet. It can't truly be based on what they originally invest, although that is a variable that's involved, but who made the smarter investment. So what we need to do is we need to relate these investments to each other as if everybody had invested the same amount. Who would have gotten back the most if they all invested in the same stock? So first we'll look at finding the relative change for myself. Also relative error, that's another way of looking at it. So the relative error formula is the actual change over the original value. So for me, that actual change was $80 and the original investment was $140. When I put this in my calculator, I get 0.57 approximately. If I was going to make this a percent, we would call this a 57% increase. So I'm going to put that right here. If we look at Jamie's, she originally invested $500 and her actual change was $150. If I put this in my calculator, I get 0.3, 30%, again, increase. And then the last one we're looking at is Tracy. Tracy's actual change was $100,000 and her original investment was $1 million. So if you put that in the calculator, it's going to give you an approximate 10% increase. According to the relative change, you can see that I put myself in the column that has the best return rate, even though I invested the smaller amount of money, which is, great and not great. So if I had $1 million when I started off with, and my end value of that would have been $1,570,000. So you can see how that's like a $500,000 difference, which would have been a great return for Tracy. Looking at the next page, we have several different examples of when you can have a percent increase or a percent decrease, also known as the relative change. Every time you do an example, you should definitely consider making yourself some kind of table like the one at the top of the page. So to show you how it works, these notes actually are kind of funny because there's a little bit of information that's not in here. For instance, it didn't tell you how much Pat invested. He invested $300 in a .com and cashed in his investment to receive $60. What was the relative change? So his original investment was $300 and the end value was $60. I take 60 and subtract 300 to get the actual change. So this time, since he lost money, our actual change is actually negative $240. And to find the relative change, remember, relative change equals actual over original. So we have negative 240 over 300. this is going to give us negative 0.8. And if I make that a percentage, we're going to say it's an 80% decrease. And that's a thing that can happen. 80% decrease. The next example, a math class increases its numbers of students by 7, putting it at a total of 22 students. What was the relative change? I'm going to actually write it up here in the table I have because this is a little bit different because they gave us an end total and they gave us an actual change. And so we have to find the original investment in order to do the relative change formula. And that's pretty easy since you know that I have to subtract a number from 22 to get 7. And so 22 minus 15 would give me 7. Now I can do my relative change formula. The actual change is 7 over 15. If I put this in my calculator, I'll get approximately 0.47. And this is a 47% increase. Joe bought a baseball signed by Pete Rose, and he spent $200 and he ended up selling it on Craigslist for $325. What was the percent increase? So you can see anytime they can ask you for either percent increase or decrease, or they can find the relative change. So the relative change here, the actual change is the difference of 325 and 200, which is 125. The original value was 200. I'm going to put that in my calculator. I get 0.625, and that is 62.5% increase. Go ahead and do the next two. Pause the video, try these out, come back, and I will reveal the answers. So you can pause it now. Okay, for the first one, we're looking at, we have an original value. So if I'm doing relative change, 34 goes on the bottom. This time it says that they ended with 15, so we say 15 minus 34, and that is negative 19. So I'm going to put negative 19 on the top of here and put this in my calculator. I get approximately 0.56, and so I'm going to say this was a 56% decrease. Notice that I didn't put a negative symbol with the 56%, because if I use the word decrease, I'm addressing the fact that it's a decrease. So once I can say the word decrease, I don't have to put the symbol in front. The next one, a shirt had a retail price of $52. It went on sale and sold for $28. What was the percent decrease? Remember, the original is 52. The end value is 28. So end value minus the original value. 28 minus 52 is negative 24. So my relative change formula is going to be negative 24 over 52. If I put this in my calculator, I get approximately 0.46, and that would mean that this is a 46% decrease. Because remember, when something's on sale, it means the price is less than what you started off with. This page is looking at rates, which is a comparison. It's expressed as a fraction with two quantities that have different units of measure. We use rates probably so much with certain things that you don't even think about the fact that it's a rate. Most popular being rate of speed, which we measure in miles per hour, which could also be written as miles over hour. Anytime you have a rate, and if there's a 1 in your denominator, then you can kind of replace the division symbol with the word per, like revolutions per minute, or I don't know, something along those lines. Other ones, there's pounds per square inch. That measures the air pressure, most likely in a tire. Other ones are miles per gallon, and most often called MPGs. Anything along those lines, that's a rate. So if we look at number 1, a car gets 33 miles per gallon. 33 miles equals 1 gallon of gas. How many miles could the car go if it has 8.5 gallons of gas in it? Now, you're probably doing this thing in your head because this is the kind of math that you live every day, and this is probably the kind of math you're not bad at. But I want you to consider thinking like this. We know that it has 8.5 gallons. We know we're going to have to multiply that by something, and what we want to do is we want to end with an answer that has the word miles next to it because this is how many miles. So what we're going to use is this rate to help us finish this off. I'm going to put a fraction bar here, and I'm going to decide if I want to put the miles on top or on bottom. And the thing is, I want to cancel out this label, but the only way I can cancel out that label is if I have that same label in the cross cancel area. So if I put gallons down here and miles up here, then I'm able to cross cancel gallons. And if these were fractions, we do what fractions tell us to do, and we multiply across the top and across the bottom. And because this was not canceled, this is allowed to be our label. And so 8.5 times 33 is 280.5. The gas tank in a Toyota Prius can hold 8 gallons of gas. You're just going to have to start to recognize when they're giving you rates. One tank is 8 gallons of gas. The Prius can get 50 miles per gallon. Ooh, 50 miles equals 1 gallon. If the car needs to drive 1,200 miles, how many tank of gas will be used? We want to end up with tank. We're starting off with miles. So I'm putting my starting value here, knowing that whatever I multiply this by, it has to have the word miles in the bottom so I can cross cancel and get rid of miles. The only rate I have here that addresses miles is this one, so I'm going to put 50 miles, 1 gallon on top. The thing is, I don't want to end with the label gallon. I want to end with the label tanks. So I'm going to multiply this by yet another fraction, and I just know that I want to have gallons on the bottom so I can cross cancel gallons, and hopefully tanks on the top so I have the word tank as part of my answer. And so this tells us that 1 tank equals 8 gallons. So now I cross canceled miles, I've cross canceled gallons, and I am left with tank where I want it. If I multiply across the top, if I multiply across the bottom, I get 50 times 8, which is 400, and 1,200 divided by 400 is 3 tanks of gas. A nice tidy answer. So we've already started looking at unit analysis, which is it's a guide. When you want to set up a calculation that is handling more than one rate, you use unit analysis. If the calculation is set up correct, then your answer will have the appropriate units of measure. Like I said before, the things that you're starting off with are what you are asked to convert, and then what you're asking to convert it to. Those are the things that you need to start setting up your equation. Diane has 8.3 gallons of milk. There's our starting value. She must repackage it in liters. So we know that 1 gallon equals 3.79 liters. I'm going to put what I'm starting at first. That's 8.3 gallons. My 8 looks awful. I know whatever I multiply this by, I want gallons on the bottom. I have 1 gallon equals 3.79 liters. So I can cross cancel gallons, multiply across the top. 8.3 times 3.79 is 31.57. So 31.5 liters. 31.5 liters. This is a thing because not really looking at milk as much, but if you've ever been in Canada, they use the metric system. So when you cross over, the speed limit signs stop saying 65 and start saying 100. And it's because they've stopped measuring length in miles and they've started using kilometers, and kilometers are shorter than miles, so you can go more of them and still be under the speed limit. They also sell gas in liters. So liters are much smaller than gallons. So liters are much less money because there's less gas in a liter, right? So if you go to the gas tank and it might say $1.10 a liter, and you just see $1.10, you think you're getting away with something, but then when you get there, you'll be shocked at how quickly the meter goes up, because for every 3 liters is 1 gallon. So you're getting like 60 liters, and so you're going to end up paying the same amount of money that you would have paid in the States. And it's just confusing all around, but kind of a good confusing, because, I don't know, it opens people's eyes up, I guess. Okay, Sally measured her hallway to be 5,245 centimeters. Her husband wants her to convert that to feet. I'm going to give you a minute or 2 or 5 or 10, because you're the one on the pause button, to do number 2. And then I'm going to come back and do it with you. So you just need to pause right now, please. Okay, so we're starting off with 5,245 centimeters. We know we want to end with feet. The only unit, or the only rates I have that have centimeters in it is this first one, so I have to use this one. 2.54 centimeters are in 1 inch. Cross cancel centimeters. Then I need to cross cancel inches, so I'm going to put 12 inches down here equals 1 foot. And I'm going to cross cancel inches. If I multiply across the top, I multiply across the bottom, I know I can put feet after this. I just have to put this little lovely-dovey thing in my calculator. And when you do that, you'll get approximately 172 feet. It is like the world's longest hallway. This last one always makes people either cringe or not cringe. I don't know. There's no rates given here, because you should know a lot of these rates. We're starting off with days. We're ending with seconds. You just have to recall all the things you know. Like, 1 day has 24 hours. We are not at seconds yet. 1 hour has 60 minutes. Cross cancel, cross cancel. 1 minute has 60 seconds. Cross cancel minutes. And I put my calculator 2.5 times 24 times 60 times 60. And this is what we get. 216,000 seconds. Oh, we still have more. How many furlongs is 2,800 yards? Okay, so I've just realized again that I have neglected to put rates in here. So give me 1 sec, I'll take a picture of it. There you go. There it is. Okay, so you've got probably more conversions here than you need, and this is usually a thing, because books are published and they don't know what you need, so they give you everything. This is what we know. We know we're starting with yards, and we know we want to end with furlongs. So here's my yards. I'm going to multiply this by something that has yards on the bottom of it. Things that I could do, I have yards in this one, I have yards in this one. All I know is that I'm eventually going to be getting to furlongs, and the furlong thing I have is connected to rods, so that means I'm going to use this one. So I have 5.5 yards. 1 rod goes on top, so that helped us cancel yards. Now we want to cancel rods. We got 40 rods in 1 furlong. So cross cancel rods. Now I just have to put this in my calculator after I multiply across the top, 2,800, and across the bottom, 40 times 5.5 is 220. I know that when I put this in my calculator, I might as well just set up my cute little label now. Let me just grab the calculator. Approximately 12.7 furlongs. I guess the idea here is I'm trying to give you different problems that don't use the same measurements that you're used to. And this stuff obviously is looking at other types of measurements, things that deal with being on the water, stuff like that. So go ahead and try number 6. You can pause, and then when you come back, I'm going to go over it with you. Okay, we're starting with inches. We're ending with nautical miles. Oh goodness, nautical. I have to look up here and decide what it is that I'm going to be using, erasing all my old stuff that I had there. Okay, so inches, I have this here. Well, that's the only thing I have with inches, so I'm going to have to use that. 12 inches is 1 foot. Okay, and I'm trying to get to nautical miles. Ooh, we have one here. Feet to nautical miles. There are 6,080 feet in 1 nautical mile. So if I multiply across the top, I have 23,500. And if I multiply across the bottom, I have to multiply 12 times 6,080. Notice that I have cross-canceled inches and cross-canceled feet. Putting this in my calculator. Let's take a moment. 0.322 nautical miles. Another one I want you to try on your own using crazy measurements, ruggies, figs, tillers, smuggles. Go ahead and take a moment and do this one and come back and we'll reveal the answer. Okay, 4.5 ruggies. Without even looking, I know that I need ruggies on the bottom to cross-cancel ruggies. Ooh, that would be this one here, right? 4.5 ruggies is 2 smuggles. It's like a Harry Potter thing. I'll put smuggles down here. Get rid of those. Okay, so this one right here is the smuggles one. 14.2 smuggles is 1 fig. And then I have the conversion for figs to tillers. Fig to tiller. 3.2 figs is 5 tillers. Cross cancel, cross cancel, cross cancel. When you multiply across the top, I'm going to be multiplying 4.5 times 2 times 5. On the bottom, I'm going to be multiplying 4.5 times 14.2 times 3.2. Whatever I get, I can put next to the thing, tillers, and I'm going to go multiply that. Approximately 0.055 tillers. Yeah, let's go to the next page. All right. We're completely shifting gears and going somewhere else. I need a drink of my iced coffee. Okay, we're going to look at powers. So we're completely putting aside what we were just doing and going in a completely different direction. Just to go over some things you probably already know. Whenever you have a power, we call this big number the base, and we call this small number the exponent, and the entire package is called a power. The thing about powers is, this is another one of those things that people can very, very easily make an error on. Whenever you have an exponent, it goes with the base that's immediately next to it. For instance, the base is -5 because everything is in parentheses. I multiply -5 by itself twice according to my exponent, and a negative times a negative is positive. For B, here's my negative symbol, but the 2 is not going to apply to the negative symbol because there's no set of parentheses including it. The 2 only is going to apply to the 5, and so this is giving me a different answer than the first one. People would think that's not a thing, but it is a thing. C, just a different thing. Remember that whenever you're simplifying a math equation, you have to do the exponents. Ooh, changed my marker. 3 minus 4, 2 times 2 is 4, is -1. I don't like that. I want my pencil back. Okay. Anything raised to the power of 0 x to the 0, 5 to the 0 is 1. Believe it or not. Anything raised to the power of 0. It doesn't matter if it's some crazy thing like this. If it's raised to the power of 0, it's 1. I guarantee, though, when I come back, what if something is raised to the power of 0, what is it? And somebody is going to say 0. Because that seems like the right thing. But it's not. Now let's talk about negative exponents. A lot of people think that if you have an exponent that's negative, it means that the entire number must be negative, but that is not the thing. The thing that can determine if a number is negative is if there is a negative symbol in front of the number. That's what would make it negative, but that's not the case. If you have a negative exponent, it usually means that your quantity is much smaller. Like it's like a fraction of a thing. And I'll show you. Whenever you want to write something that has a negative exponent as something with a positive exponent, you have to draw a fraction bar. Right now, we know that this could be expressed as a fraction if I put it over 1. But I'm going to actually have to move the power and with the negative exponent and the basis immediately with it to the other side of the fraction bar. There's still a 1 up here, but when this goes to the other side of the fraction bar, that 2 now becomes negative. And if I was going to write this as a completely simplified number with no negative in the exponent spot, it would look like that. What happens with b? So I'm still going to put my fraction bar here. Y has a negative exponent. X doesn't, because x's exponent is positive 1. So the y is going to come down, and I'm going to rewrite this as x over y to the positive 2. For c, notice that we have a negative exponent here. You have to move it to the other side of the fraction bar to make it become a positive exponent. So that would look like this. If you put that over 1, it wouldn't be wrong. You're writing too much stuff, but it wouldn't be wrong. Okay, let's look at the next page. We're back on scientific notation. Way back when we first started doing this, I was telling you that scientific notation refers to really, really large numbers or really small numbers. So I have some very small numbers. If I were to look at a number like this and write it with scientific notation, remember from the past, you want to move that decimal so that it has one non-zero digit to its left. So this would start off looking at like 3.450 times 10 to what power? Well, I got to count those jumps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 jumps. But because we're jumping to the right, because this is a small fraction of a number, that 11 is going to be negative. That's correct. It's going to be negative. Go ahead and do A and B, and I'm going to give you the answers to those. Pause. Okay, for A, move my decimal 3 units to the right. 3.210 times 10, 3 jumps, negative 3. For B, 1.844 times 10, we had 1, 2, 3, 4, 5, 6, 7, 8 jumps, negative 8. Here we are. Now we have something in scientific notation. I haven't had anything to drink either. I haven't drank alcohol in a really long time, and you can tell because I'm still slurring. 5.66 times 10 to the power of negative 7. I'm going to write 5.66, and I'm going to move my decimal 7 units. If you ever forget which way, think this is implying we have a small number. If I move my decimal this way, it's going to make my number really big. So I am going to move it this way. 1, 2, 3, 4, 5, 6, 7. In order for this to be possible, I got to stick some zeros in those jump spots. And there it is, standard notation. Go ahead and do A and B, and then I will look at them with you. The first one, 1 0.722. I have to move my decimal 2 units to the left. There it is. And then 8.362. 8 digits. 1, 2, 3, 4, 5, 6, 7, 8. Oh my God. 0, 0, 0, 0, 0, 0, 0. I'm thinking there should be 7 zeros, right? And this one, there should be 1 0, because usually one of these numbers is used up for that first number, and then you have to fill the rest with zeros. So I kind of use that as a way to check and make sure my answer is correct. Okay.